Hello everyone, welcome to the kinematics and dynamics of machinery class. Today we're going to continue the topic that we started in the previous video, the previous meeting, which is the graphical solution of the kinematic analysis of mechanisms. We have discussed the position analysis and we practice how we can, and we discussed the four cases of the position analysis using the graphical method. Today we're going to continue the same topic, but we're going to consider more the velocity, the acceleration, and the acceleration analysis of mechanisms, right? So to explain this, I'm gonna give you the lecture note number 5, and in this lecture note you're gonna find like a comprehensive explanation of the different cases that we would experience for the velocity and the position analysis of different mechanisms, how we can generate the velocity polygon and the velocity and the acceleration polygon of these cases, different cases. But to explain these cases to you, I decided to work over these two examples. You could consider that they cover most of the cases that we are interested with through this course. So I'm gonna start with example 1. I'm gonna do the position analysis, then I'm gonna move and I'm gonna show you how we can work on the velocity analysis, then the acceleration analysis, then I'm gonna repeat the same for the second example. This is typically what we're gonna do through today's video or lecture. So, starting with example 1, it is simply a crank slider mechanism that will have the crank O2A, and there is a connecting link which is AB, and there is a slider that slides over the horizontal surface, but there is offset distance here with 1.5 inches as already given, and this angle is given by 30 degrees in addition to some dimensions, in addition to the angular velocity of this link O2A, which is given by 30 radian per second, and the angular acceleration, which is given by 150 radian per second square, and both they are rotating in the same direction, which is counterclockwise direction as already given up there. So these are the given data, and again we are required to do a complete kinematic analysis of this mechanism, and let us see how we can do it. So in the beginning, let us start with the velocity analysis, but before we start, what you're gonna do, you just need to have one white drawing sheet. Make sure that all the position, velocity, and the acceleration diagrams or polygons will be represented like we start with the position, velocity, and the acceleration polygons. All of them should be represented over the same drawing sheet. So I'm gonna use this one as a drawing sheet, and I'm gonna keep this one on the side, and this is I'm gonna do all the other calculations, all the other, like plan. We, as you gonna see now for the velocity and acceleration analysis, we're gonna like plan how we are going to draw these velocity polygons, acceleration and acceleration polygons. So we're gonna put the plan and all the details and all the calculation, we're gonna put it here or over these drawing sheets. But this one, we're just gonna save this one just for drawing. Everything, all the polygons should be represented over the same sheet. It is not possible for you to represent the position polygon in one sheet and the velocity polygon over another sheet, because you need the position polygon to generate the velocity and acceleration. So all of them should be represented over the same sheet, as I'm going to show you. So in the beginning, we're going to work as usual, and I'm going to start with the position analysis of the mechanism. And as usual, the first step conventionally is just to define the give numbers to the different elements. So we do have the base or the ground, this is the frame, which is element 1. In addition, we do have element 2, which is this link that do rotation about 0.02. In addition to the AB, this is the third link number 3, and the element number 4, which is just a slider. So these are the 4 elements that we conventionally have for a crank slider mechanism. Then what we're gonna do is just to set up the position vectors as usually we do. So starting from O2 to A, this should be position vector 2, right? So this is, let us assume that this is R2 vector, right? And from A to B, we do have R3 vector, which is this position vector as R3 vector. And definitely we have to set up a position vector for the slider. This slider is moving over the horizontal dimension, right, direction. So it means that there should be R4 vector, and this R4 is working for the slider itself. So as you can see, we end up with a loop, but this loop is open loop. So we have to close the loop with an additional position vector that we additionally gonna set up this one here as R1 vector, where one this should be the, you know, like this one, it should be the ground. So we're gonna end up with 4 position vectors, R1, R2, R3, and R4, and we can give even a name to this point like point O. This is the virtual point that is the intersection point of R1 with the R4. Make sense? So these are the different position vectors that we use to define. Even you can work over this given problem, or you can redraw again the mechanism and allocate these different, or define all of these different position vectors. It doesn't matter whatever you're gonna redraw again, or you're gonna use the same drawing that is already given to you. But anyway, your objective is just to specify these given data, which is given, which is unknown, in terms of R1, how much it is, in terms of theta 1, and in terms of R2, theta 2, and in addition R3 and theta 3, and R4, theta 4. Make sense? So R1, it should be the distance between O to O2, which is already given by 1.5 inches. So it is already given. Remember that we are limited for just 2 unknowns. Theta 1, it should be 90 degree, right? Which it should be this angle is already given by 90 degree. Why? Because you should define this angle from the start point, draw a line to the right, rotate counterclockwise till you hit the R. This is going to give us the R1 or theta 1. R2 is going to be the same. R2 should be O2A, and AO2 is already given by 2.5 inches, so it is 2.5 inches. And theta 2, the angle is already given by 30 degrees, so it should be 30 degrees, or as given. As usual, from the start point, draw a line horizontal to the right, rotate counterclockwise till you hit the R. This is going to give us theta 2. R3, it should be the AB, and RAB is already given by 10 inches. And we do have theta 3. Theta 3 should be this angle. If from the start point, which is this point A, rotate counterclockwise till you hit R3, this should be theta 3. But unfortunately, this theta 3 is unknown. So this is the first unknown that we have. We have no clue how much it is. And if we move to the R4, it should be the distance between O to B, but this distance is not given. So it is unknown here. There is no OB already given there. So it is unknown. Theta 4, it should be 0 and degree, because it is horizontal going to the right as already given here. So we end up with these 2 unknowns, and this is gonna define one of the cases, the 4 cases that we discussed in the previous video, right? Even it is not important to know what is the case, as we demonstrated in the previous video. The key idea is that we do have 3 cases of the position vectors. That the case that the position vector is fully defined, or it has missing direction or missing magnitude as already given here. So we do have the 3 cases already combined in this example, as I'm going to show you. Then what we're going to do, we have to define a scale for all of these dimensions. As you can see, the given dimensions are in inches. So an inch, if you decided to convert to millimeter, the inch equals to 25.4 millimeter. But it is not advised to do conversion of the unit. Stick to the unit and just get on with the same unit here, but just do scaling. So if you just observe the different values here, we do have 2.5, assume this is like 2.5 millimeter, which should be too small value, and we do have the 10. So I'm gonna work on the scale, like let us assume that the smallest dimension, which is 2.5, I'm sorry, the smallest dimension actually is 1.5 inches. So I'm gonna assume that this 1.5 inch, I'm gonna draw this one like 30 millimeter, for example. Like 30 millimeter is a good number, like because it's 30 millimeter, it is 3 centimeters, so you can easily clearly see the line of the position vector. But you can assume any other value like 20 millimeter, 25 millimeter, 15 millimeter, it's up to you, right? But anyway, we do have 1.5 inches, and I'm going to assume that I'm going to draw this one at 30 millimeter. So, but in addition to this 1.5, we do have 2.5 inch, and we do have the 10 inches, right? So what should be these values in the drawing? This is the drawing side as we agreed, and this is the real side, right? So in the drawing, what I'm going to do, just do the multiplication of 30 times 2.5 divided by 1.5. This should give us this number here. So if we did the multiplication at 30 times 2.5 divided by 1.5, this is going to give us 50 millimeters. So what does it mean? It means that the 2.5, I'm going to draw this one as 50 millimeter. And the same for the 10 inches. If you did the multiplication of 10 times 30 divided by 1.5, so 10 times 30 divided by 1.5, this is going to give us the 200 millimeter distance, right? But you have, it is a little bit tricky here because I end up with 200 millimeter. And as you can see, this 10 inches, it should be for the R3, and R3 it has a missing direction. It means that we said that for the position vector with a missing direction, we have to use the canvas, right? So it means that you should have a canvas that can be open. You should have a canvas that can be open up to 200 millimeter. So if we try, this is the canvas that I'm using, and if I try to open the canvas with 200, it can only be open up to 135, for example, 135. It means that I cannot use the 200. The 200 is a huge number here. So it means that you have to do changes into the scale. It means that you assume 1.5 inches and you decided to draw this one at 30, it won't gonna work. So it is, at least I have to break down this scale or to scale it down into the half. So what I'm gonna do here, I'm just gonna do changes and I'm gonna multiply times 0.5. I'm gonna divide all of these scale values into the half. So I'm gonna end up here with 15 millimeter. Here it should be 25 millimeter. Then I'm gonna have 100 millimeter. Now I can manage. I can draw because I can open the canvas with the 100 millimeter. But in the beginning, the 200 was big number in this case. So just simply scale it down into half of the 30, half the 50, half the 100. So we already end up with the scale, and this is the dimension that we're going to use for the drawing. Mean that the 1.5 inches, it will be represented by 15 inches, and so on for the 2.5 and the 10 inches will be represented as 100 millimeter. Make sense? So this is for the scale. In the previous video, we generated we draw the position polygon over the same sheet. No, don't do that. Why? Because you have to draw, you have to use a separate sheet, and all the position, velocity, and acceleration polygon should be represented over the same sheet, right? As I just mentioned. So I'm gonna stop here, and now I'm gonna move to the drawing sheet. This is the sheet that I'm using, right? Now I'm gonna bring the drawing sheet, which is this one, and I'm gonna start working on the position analysis. So I'm gonna start here with the position polygon. This should be the position polygon that I'm going to generate. Make sense? So in the position polygon, or to do position analysis, as usual, your objective is just to start drawing the vector that already fully defined or completely defined, which are the R1 and R2 as already given here. So starting with the R1, it has a length of 1.5 inches, which should be represented as 15 millimeter, and the angle is 90 degrees. As we agreed that the position vector, it should be represented or drawn over 3 steps. The first step, just measure the angle. The second step, draw a light line over this angle. Then over this line, you're gonna measure the distance, which is 1.5 or 15 millimeter. And this is what I'm gonna do. But it is advised to have like a general reference for you that is a line that is horizontal in the drawing sheet. In this case, is just try to align one of the edges, the edge of the sheet with one of these lines, and draw a horizontal line, very light line. This is a reference horizontal line, and we're gonna have another reference line that it should be perpendicular in this case. Make sense? Then I'm gonna try to draw the position polygon here, leave space for the velocity and the acceleration polygons down there, right? So I'm gonna try to stick up a little bit, and keep in mind that if you decided to start from point O2, for example, or point O, we do have either, because R1 is set up between O or O2. So it's up to you. You can start from either point O or O2. I can start from point O, for example, to locate point O2. So I'm gonna start from any point here, and I'm gonna assume that this is like point O2, point O, right? And from this point O, what I'm gonna do, I'm just gonna draw a vertical line as we agreed. I'm gonna draw a vertical line that is parallel to this edge here to make it vertical, and Why vertical? Because the angle is 90 degrees. So this is, looks like you already measured the angle. Then I draw a light line. Over this line, I'm going to measure the length of R1, which it should be 1.5 inches, which it should be represented by 15 millimeter. So I'm going to measure here 15 millimeter over this line. So it is 10 and 15 millimeter. Mark a point. This should give us the O2 point. And then if we're going to go over this line again between these 2 points, this should give us the position vector, the first one, which is R1 vector. Make sense? So we got the first position vector. Now let us move to the next one. The next one, so we got this one. We got this R1. Now we're going to move to the R2. R2 is also fully defined. It has an angle 30 degrees, so we have to measure the angle first. But you should understand that this position vector is set up between 2 points, point O2 and point A. In this polygon, we do have so far just point O2. We have no clue where is point A. So from point O2, I'm going to draw this position vector with an angle 30 degrees. So from O2, from point O2, simply I'm just going to use, or even you can directly measure the angle of 30 degrees in this way. Like from this point, try to have I'm using this line to be parallel to this line. Also, I'm aligning this vertical line, black line of the triangle, to the vertical line here to make sure that this line is horizontal and this is completely vertical. Then I'm gonna measure 30 degrees in this direction. So this 30 degrees, it will be 10, 20, and 30, and mark a point. Even though if it is over the disk, don't move the drawing sheet and try to connect this point to this point to end up with the line. So we measure the angle, then we draw a light line. Over this line, you're gonna measure the length of O2A, which is R2. R2 is already 2.5 inches, which is, according to the scale, I'm gonna draw this one as 25 millimeter. So what does it mean? It means that I'm gonna measure here 25 millimeters as already given here. And mark a point. This point definitely it will be point A. So we had point O2. Now we got point A for this length, and this should be the R2. This should be the R2 vector, as we already defined this vector up there. Make sense? Once we defined R1 and R2, which are the fully defined, we're gonna move to R3. R3, it is a problem. It has missing information, missing data, that R3 is unknown, right? Theta 3 is unknown. Theta 3 is unknown. It means that this is a position vector with unknown direction. So we said that for a position vector with a known direction, we have to use the cams for this one. So we're gonna work over R3, and we're gonna use the cams, and we're gonna open the cams with the radius, the magnitude of this position vector, which is 10 inches, which has been converted into 1 millimeter, or we decided to draw this one as 100 millimeter. So I'm gonna open the cams with 100 millimeter in this case, right? Then from either point A or B, because R3, this belongs to the R3 vector, and R3 vector is set up between either point A and B. So in this graph, we'd have only point A. So from point A, I'm gonna draw, the objective is just to locate point B, because as you can see, we located all the points. We got point O, O2, A, we still missing the point B, and this is the last point. So using the cams, I'm just gonna fix at point A and draw a curve. And draw a curve as we agreed in this way. So this curve should be locus for point B. It means that point B should be located somewhere over this curve. Then that's it. It means that we said that for a vector with a known direction, we can only do one thing, which just drawing a curve. For the other vector with a missing magnitude, we can do 2 steps of the 3 steps. The first step, that we can measure the angle and then just draw a line, and that's it. So the angle is 0, so it means that it should be horizontal, and there is already clearly seen that it is horizontal from the mechanism, and it should be set up, this R4, it should be set up between point B, O, or B. We don't have point B, but we do have point A. So from point A, I'm gonna draw a horizontal line in this way. Make sure that you already align one of these vertical lines of the triangle with your reference vertical line. Then draw a very light line. So I measure the angle, then I draw a line. This second line, it should be locus. So this is one locus, this is the second locus. These 2 loci should be intersecting at a point. This point definitely it will be point B that we're already seeking, right? Then if you connect point B to point A, this should give us the position vector R3. right? Which we defined it in this direction as R3, and this should be the R4 position vector as we agreed. Make sense? So we already done, we finished the position analysis, or to be accurate, we finished the position polygon, but we still need to find the unknowns here. So we're gonna go back again to the writing sheet. This is the writing sheet, this is the drawing sheet, and keep this one on the side here. In the writing sheet, you're gonna say that from the position polygon, what are the missing data here? We are missing R4 and theta 3. So let us work over R4. R4, it should be the distance between O and B, right? So, and we already got it here. So simply from the drawing sheet, if you just measure the distance between the O and B, we're gonna get it here by 116 or 17. It is in between 116 and 17. So let us say that it is 116 millimeter, right? This is how we're gonna get it from the drawing. This is from the drawing. We have to convert it into the real value. So it's equivalent real value. Assume that you're already putting the 116 here over this side. So you're gonna do the multiplication. So what should be this value? You're gonna do the multiplication of 116 times 1.5 divided by 15. So this is gonna give us 116 times 1.5 divided 15 to inverse or to scale back again to the original dimensions. So if we did the calculation, this is going to give us 116 times 1.5 divided by 15 gives us the 11.6 inches. So this should be at the end the exact value of the, not exact, this is the real value that we need for the position vector 4, which it should be very close to the analytical solution value. Then we have to do measurement of the angle, and remember there is no scale for the angle theta 3. And this angle, it should be, as we defined here, theta 3, it should be this, all of this is just the angle, but we can simply measure this angle between the horizontal line and the inclined line. This is what I'm gonna do. From this point A, I'm just gonna fix here, try to align one of these lines to be parallel to the vertical line, to make sure that it is, this edge is completely horizontal, and, no, sorry, my bad, I should measure in this way. Should be here aligned, and make sure that this edge is completely horizontal. Then your objective is just to measure this angle. This angle, it should be this, if you can see, there is the R3 line, right? Because I'm measuring for the R3. So R3 is already going down here. This angle, if you can observe over the protractor, it will be like 10, 15. It's gonna be exactly already over the 17 degrees. So this angle, this a little bit small angle, it is 17 degrees from the graph, which is already here 17 degrees. So it means that theta 3, it should be the 360 negative the 17 degrees if you decided to represent theta 3 in as rotates counterclockwise direction. So it should be 360 negative 17 will be 343 degrees. This is for the missing data for the position parts. And this means that by finding these unknowns, it means that we already finished the position analysis graphically for this mechanism. Make sense? Next, what we're gonna do. So basically, we already covered and discussed all of these parts previously in the previous video. The new thing here, that this is what we're gonna do here for the velocity analysis. So now we're gonna move to the velocity analysis of this mechanism. And for the velocity, and the same is going to be for the acceleration analysis, your objective is just to put a plan. Before you go to the drawing and creating or generating the velocity and acceleration polygons, before using this drawing sheet, you have to put a plan. You have to write some equations here, as I'm going to write I'm going to show you now. This equation is gonna give you like a plan, what exactly that you are going to do for the velocity polygon, and the same for the acceleration polygon. So now let us focus on the velocity analysis, and this is gonna be the second step in the velocity analysis. And for the velocity analysis, as we did for the position analysis, we're gonna consider some important cases. Through this example, we're already representing 3 cases, and in the next example, we're gonna consider the 4th case, right? As we did for the position analysis, we said that we do have 3 important cases of the position. that it would be fully defined, so it is, you're gonna apply the 3 steps. It would be with a missing dimension, so you're gonna apply only 1 step, or it would be with a missing magnitude, so you're gonna apply 2 steps, right? We're gonna do the same for the velocity, but here we're gonna consider 4 important cases. The first one, that you have a link that rotates about a fixed point like the link O2A, and a link that do general motion, that fixed link like with a fixed length like AB, and this link has no fixed point. Or the third option, or the third case, that you have a slider that moves on the ground, either horizontal, vertical, or even over inclined surface, but anyway just a slider that moves. This is the third case. The fourth case, which is already in the second example, in case that you have a slider of a link. So these are the 4 cases, and these 4 cases are explained in detail in the lecture note number 5. But I'm gonna go over these 4 cases through these examples here. This is what we're gonna do through this video, okay? So here in this example, we have the first 3 cases that we're gonna consider them. The key idea is to start. First of all, we have to start from the link with a given data, with the given information regarding the velocity. Now we are working on the velocity. All the velocity data are given for link O2A, which is link 2, or the position vector 2, right? So for link 2, this is the link that I'm gonna start with. Then keep going till you finish the other links or the other elements within the mechanism. Conventionally or generally, we do have in this mechanism 3 options, 3 objects. We do have the link 2, we do have the link 3, and the slider. But how about R1? R1, it is a virtual thing. There is no physical link that already set up parallel to the R1. We just close R1 to close the loop. We define R1 to close the loop, right? But for this mechanism, we have only 3 elements, which are the link O2A, which is, we give it number as 2, so this is link 2, link 3, which is AB, and the slider, which is slider number 4, or slider B. These are the 3 elements. Your objective is just to write, forget about the drawing for now, just write an equation for each one, or put a plan. This equation is gonna be like a plan. You are already putting a plan how you're gonna draw the velocity line for all of these elements within the velocity polygon. Make sense? So we're gonna work on over all of these 3 elements, but starting from the element that you already have given information, or information that given to it, which is link 2. So I'm gonna start with link 2, and link 2, generally it is a link that do rotation about a fixed point, which is point O2. This drawing there is no need to draw, but here just I'm explaining something to you. So I'm just gonna use this representation to give you more details about this link 2. So link 2 is already set up between 2 points, point O2 and point A. Make sense? And there should be the position vector, which is R2 vector. And the omega 2, here we are interested in the omega 2. This is the angular velocity of this link, which is already given. So then your objective is just to start writing the equation as we did in the dynamic class before for the velocity vector for this link, right? So this is the first case that we have a link that rotates about a fixed point. So this link again, it is set up between 2 points. So we're gonna say that the velocity of point A equal the velocity of point O2 vector plus the velocity of A relative to O2 vector. This is, if you remember from the dynamic class, this is the equation that describes the velocity of the two, or the relative velocity between these 2 points that define this link, right? If you remember, we said that if we mentioned A, then O2 have to mention A, then A2. But this one, it looks like moving from O2 to A. Forget about the movement for now, but if we mention AO2, so it should be AO2. Stick to the order, right? We can rewrite this, we can write this equation in another form by moving O2 outside and A to be on the left and the right side. So, but we have to switch here as well. It's gonna be the same equation. It's gonna be the same equation for the same length. So it means that we're gonna end up with the same result. But conventionally, even if you remember from the dynamic class, we mentioned in case that you do have one of the point is fixed point like point O2, it is better to keep this one on the right side and keep this VA on the left side, because we are interested in finding VA, how much it is, because we are pretty sure that this velocity is already 0. This is a fixed point. Make sense? And another thing, so this is the equation. And remember, to draw this velocity vector or to draw this velocity in the velocity diagram, it should be drawn from either point O2 or A. From either point O2 or A. Depends on which one of these 2 points already located in the velocity diagram, as I'm gonna show you now. But another thing, basically, when we draw over the velocity diagram, we just draw relative velocities. We are not drawing absolute velocities. So what does it mean? A is absolute velocity. VO2, it is absolute velocity, but it is 0 because O2 is fixed point. But if in case that O2 is not fixed point, is movable point, so VO2, it will have a value, right? But anyway, this is absolute. This is absolute velocity. This is also absolute velocity. But this one is a relative velocity. This is the relative velocity, right? In the velocity diagram, we only draw relative velocities. We are not drawing this one, we are not drawing this one. We just drew this one. So here, remember that we're still working over the first length. So this relative velocity, it has an equation which is commonly known that VA relative to O2 vector. You should understand that this is, we're still working over the same length. It should equal to this VA relative to O2, A relative to O2, it should be set up between, it is related to the position vector R2. So it should be R2 omega 2, this is its value. This is the value. Forget about the direction for now, right? Because this is a vector quantity, so it needs value, it needs magnitude and direction. So its value is R2 omega 2. And its direction, it should be perpendicular to the R2. It should be perpendicular to the R2 vector. Follow the direction of omega 2 as we did in the analytical analysis. So the things that we mentioned in the analytical analysis or the complex algebraic method that we used to add and define in the complex analysis, we're going to use them here. But here you have to memorize these things. You have to remember that in case that you have a link that rotates about a fixed point, its relative component or its relative velocity, it is r omega 2. What is r? This is the r of the link. Omega, this is the angular velocity of the link. That would be given or it would be unknown. It depends. If it is given, you're going to substitute with the values and you're going to end up with a number here. If it is not given, so it will be one of the unknowns. And the direction. For this relative require two information, two things, magnitude and direction. The direction we knew even from the dynamic class, we knew that this velocity should be perpendicular to the R2 and follow the direction of omega 2. Very simple. It is fixed. You have to memorize these things, right? So if I ask you how much is R2, any theta 2, you should have their values because we already done and finished the position analysis. So any missing dimension, thetas or R's are already given, right? So R2 now, it is 2.5. R2 it is 2.5 inches. So the question is, should I convert this 2.5 into 25 millimeter? No. Now I use this scale, these data, I use them for the position analysis. Once you finish the position analysis, forget them completely. Work over the original dimensions. So originally, R2 should be 2.5 inches times omega 2, which is already given here by 30 radian per second. So it is already given by 30 radian per second. If you did the calculation, this is going to give us a value. This is the value of the velocity vector. This is the direction of the velocity vector that it should be perpendicular to R2, follow the rotation of omega 2. Make sense? So 2.5 times 30, 2.5 times 30, this is going to give us 75 inch divided by second. This is the velocity for this length. Make sense? So this is the first length and this is the plan. I put it a plan here, right? This is the equation. The thing that will be drawing is this thing. This is VA relative to O2. This is the thing that you are going to draw, right? But another point that you should understand about this relative velocity is VA relative to O2, it should be drawn from either point A or point O2. It depending on which point is already located in the velocity diagram. Generally speaking, in case that we do have any point like point O2 has zero velocity, it should be considered to a point that we're gonna give it a name as OV. What is OV? This is the origin of the velocity polygon. So what does it mean? It means that any point within the mechanism with a velocity 0, it should be coincident to this point. It should be over this point. Or OV, this is a point that represents any point within the mechanism with a 0 velocity. This is the original point. This is the 0 point. Make sense? So what does it mean? It means that if you already given, here we didn't draw anything in the velocity diagram, right? So which point do you think that we already have? The first point that you have is point O2. Why O2 we have? Because O2 will be considered to the OV. The first thing that you're going to do when we start drawing, you're going to define the point OV. What is OV? Again, this is the original point of the velocity polygon. Any point with a velocity 0 will be considered, will be the same point OV. So what does it mean? It means that O2 will be considered to the point OV. So it means that this one should be drawn, will be drawn from point O2, which is already point OV. Make sense? So here I put a plan. Here I know exactly how could I draw this velocity vector. This velocity vector, which is this one, it requires magnitude, it requires direction, and it requires a start point. From which point you are going to draw this velocity polygon, right? So this is what I've did for the first link, which is link 2. I'm gonna repeat the same for link 3 and the slider. Here we are drawing for the elements, for the components of the mechanism. So I've done with the first link. I'm gonna move to the next link, which is R3. I'm gonna do the same. I'm gonna write an equation and put a plan as I did here, right? So moving to this to the next link, which is link 3. Link 3 is set up between 2 points as already given here, right? Point A and point B, right? So I'm gonna write an equation, and this link is a link, and this is the second case. This is the second type. The first type was a link with a fixed point. Now we are talking about a link that moves general plane motion. That it moves, it has no fixed points. And it has 2 points like point A and point B, right? And it has the, I'm sorry, my bad, it should be directed this way. The direction of this link is going down, right? And there is set up between B and A in this way, and this should be R3 vectors. Make sense? So if I ask you to write an equation for this link, you're gonna write the same equation. This one was between O2 and A. Here we are working between A and B. So I'm gonna write this equation. It should be like VA. You can start with VA or VB, it's up to you. I can start, for example, with VB vector equals VA vector plus VB relative to A vector. Make sense? Plus VB relative. If you decide to start, I can write this same equation but in a different way. I can write this equation as VA equals VB vector plus VA relative to B vector. Stick to the order AB, AB, BA, BA. Very simple, right? The components that should be drawn are these two, this one or this one, but you have to use either one of these two equations, just one of them, not both of them. So for example, let us proceed, for example, with the first one. So it means that I'm gonna work on the VB relative to A vector, right? So I'm still working over the same link. VB relative to A vector, you should understand that this should be the R times omega. This is the magnitude and its direction. It should be perpendicular to the R, rotates in the same direction of omega 3. Here we are working over R3. This is length 3. So it has R3. So this should be R3 omega 3. What is omega 3? This is the angular velocity of length 3, but it is not given. So this term is unknown, and this is the first unknown. Remember that in the velocity analysis, we are limited for just 2 unknowns. This is one of them. Why it is unknown? I knew R. I do have a value for R3. Yes, it is 10 inches, but you have no clue how much is omega 3. So this term is unknown. The magnitude is unknown for VBA relative to A. But how about the direction? We are pretty sure that the direction, it should be perpendicular. You have to memorize this. It should be perpendicular to the R3. It should be perpendicular to the R3 vector and follow the direction of omega 3, which we have no clue how much is omega 3 yet. Even its direction, we have no clue how much is its direction, right? But this is the plan. like this is VB relative to A. It is unknown. This is one of the unknown, but it should be perpendicular to R3, follow the direction of omega 3, which we have no clue how much is omega 3, and even we don't know what is its direction. Make sense? Also, you should understand that this one, it should be drawn from either point A or point B, depending on what, depending which one of these 2 points will be located first in the velocity diagram. As I said, we start from the length that is fully defined, that the data already given, the velocity information already given for this length. We start with this length. Once we finish this length, there are some more points will start to show up. If one of these points is point A, so I'm gonna start drawing this one from point A. If it is point B, I'm gonna start drawing this velocity vector from point B, as I'm going to show you. Make sense? This is the second case, and this is for the next link. The last case, or the last link in this case here, on this example, is the slider. So now we're gonna move to the slider, and remember that the slider, it moves horizontally, slides over a horizontal surface with point B. So if I ask you, and this, we define for this slider a position vector which is between 2 points, point O and point B, right? This is R4, it is set up between 2 points, point O and point B. So it means that we do have, this is R4. So if I ask you to write the equation of this position vector, the velocity vector for this slider, it should be VB vector equals VO, because it is set up between O and B, VO vector plus VB relative to O vector. Again, we just draw the relative thing, but you should understand that VO is already 0. It means that in the diagram, in the velocity diagram, point O will be considered to the original OV, to the original point OV. Make sense? As I'm going to show you. So this is the, for this one, we are just going to draw this one. It will be VB relative to O vector. It would be drawn from either point B or point O. Definitely, we're gonna have point O, because point O has 0 velocity, so it will be drawn from point O. Absolutely. Equals. What is the expression? For example, this relative velocity was R times omega. Why? Because this is a length that rotates. Here it was R times omega, R2 omega 2, because this was a length that rotates. But this one, don't write R omega 2. This one has no formula, has no law. There is no specific expression for the sliding velocity, for the relative velocity of a slider that moves over a horizontal surface or vertical surface or inclined surface. Generally, for any slide that slides over a surface, there is no specific formula for its sliding velocity, like the case of the link, whatever, doing general motion, like this one, or link that rotates about a fixed point, that this is rotation about fixed point. For this case, we don't have a specific expression for the relative velocity. We don't have a specific expression for the relative velocity, but here there is no specific expression. So what does it mean? It means that this VB relative to O, it has 2 options. Either be given or unknown. If it is given, that is fine. You're just gonna plug the value here. If it is not given, it will be unknown, as in this case. The sliding velocity of the slider was not given, and this is gonna give us the second unknown. Remember that we are limited for just 2 unknowns. So this is the second unknown, which is the sliding velocity that we should find from the velocity polygon. Make sense? But how about the direction? For any one of these relative, you should define value and direction. Value and direction. Magnitude or value and direction. So what is the direction? It should be parallel to the R4 vector. Parallel here, it doesn't mean that it should be in the same direction or the opposite direction to the R4. We have no clue yet. But it is just parallel. Make sense? So this is, as you can see, this is the plan. This is the first thing that you have to do. You have to write these equations so you know exactly what is the thing that you're gonna do. So generally, after we finish the slide, there are nothing more. There is no more curve. There is no more objects. There is no more elements. We've done of the link, the third link, link 3, and the slider. So nothing more. So what does it mean? It means that your objective in the velocity polygon to draw three curves, three lines. One line for this relative velocity, one line for this relative velocity, one line for this relative velocity. Three lines together to define the velocity polygon. Make sense? Now I'm gonna move. So after I put this plan, I'm gonna bring the drawing sheet to work over the drawing sheet here. Then I'm gonna work over the. So the next step is just working over the velocity polygon. And I'm gonna start reading each one of these data or plan or things that I planned for here. Starting with this relative velocity. If you just read, it would be drawn from either point O or point O2. But the first thing that you have to locate a point, which is point OV. Assume that this is point OV. Point OV, this is the point that any point within the mechanism with a zero velocity, it should be over this point. It should be coincident to this point. So if we're gonna look here, which points within the mechanism that you are pretty sure that you are pretty sure that they do have zero velocity. These points are point O2 and O. But this point, all of these 3 points are moving. So what does it mean? It means that point O2 and O, they should be coincident over this point. It means that this point is O2, also this point, the same point is still point O. So the 3 points should be located over the same point OV. This is the start point. Make sense? So if we're gonna return back to the plan here, the first relative velocity or the first line that I have to draw or the first vector that I have to draw is AVA relative to O2. This should be drawn from either point A, but I don't have point A here, or point O2. I do have point O2, which is the same point at the 0 point, right? So from this point, I'm going to draw this vector with a magnitude of 75 inch per second, and the direction it should be perpendicular to the R2, follow the direction of omega 3. Make sense? You got it? So the question is, before we draw even, should we do scale? It's probably in most of the cases you're gonna do scaling for the velocity part. As you can see, we have only one value here, which is the 75 inches. 75 inches is a big number somehow. How about if I decided to draw this 75 inches like 50 millimeter, for example? So I'm gonna do scale here. I'm gonna use a scale for the velocity. I'm still working with the velocity. That the 75 inch per second, I'm gonna draw this one as 50 millimeter in the drawing. So this should be the drawing. This is the exact value. This is the real value. Make sense? And nothing more. So going back again, how we draw this vector? You have to define the direction first, then you're gonna measure the distance. It is like you already drawing a position vector. If you remember, we said that we already using 3 steps for the position vector, right? The step 1 is to measure the angle, draw a light line, then measure over this line, right? The distance, the magnitude. We're gonna do the same. But here we don't have an angle. Instead, we have a direction. The direction, it should be perpendicular, follow omega 2. Perpendicular to what? Perpendicular to the R2. What is R2? You already draw R2 here, right? So your objective from this point, you're gonna draw a line that is perpendicular to the R2 and rotates with omega 2. What is the direction of omega 2? Omega 2 is going up. So it means that from this point, I'm gonna draw a line because omega 2 going up. This is the omega 2. So I'm gonna draw a line from this point. This is the first step. From this point, I'm gonna draw a line that is perpendicular to this R2 and follow the direction of omega 2. It means that it should go up. Make sense? With a length of 50. So let us move this point since I'm using a big scale, I'm gonna move this point here, the 0 point OV, a little bit down. So I'm gonna have like more space, and should be the O2 and this should be the point O, right? So how can I draw a line that is perpendicular? This is the benefit of the Arrow triangle in this case. Make sure, do you see this line? This should be R2, right? If it is short, you can increase the length of R2 somehow. And you're gonna use the Arrow triangle. make one of these lines aligned or coincident to the R2 direction. In this case, if you draw a line here, this should be perpendicular to the R2. Then you're just gonna move till point OV, in this case, and draw a line that is going up. Very light line in the beginning. This is the direction. Now I specified the direction. From this point, I draw a line that is perpendicular. This line is completely perpendicular to the R2. So that's why you should have all the drawing over the same drawing sheet. To have this one perpendicular to this one. And it should follow omega 2. Omega 2 is going up. So that's why I went up. Why I didn't go down, I went up because this omega 2 is going up. So I have to push up the same direction following omega 2. And the value should be 75 inches. Right? But after the scaling, the 75 inches over the second, it should be represented by 50 millimeter. So what does it mean? It means that over this line, I'm going to measure distance of 50 millimeter, which is 10, 20, 30, 40, 50, and mark a point. This point, it should be the other point which is point A, because this position vector should be set up between 2 points, point A and point O2. This is already point O2, so this point definitely should be point A. Make sense? Then your objective is just to mark this line or increase, just make it clear. This should be the position vector, which it should VA relative to O2 vector. Make sense? What is the direction of this vector? It should be moving from O2 going to A. Moving from O2 going to A, so this should be the direction of this velocity vector for the first object, which is the length 2. So this is the velocity vector for length 2. Again, it is perpendicular to the length 2. It is perpendicular to the R2 in the same direction of omega 2, and the magnitude was 75 inches, which has been drawn by the 50 millimeter. Make sense? So I've finished the first element, moving to the next element, which is also a length that rotates. Okay, just move with the procedure. And here for this one, the thing that it should be represented or drawn is this relative velocity, this part. I'm just writing this equation for nothing. I mean, like, just write the equation, but you should understand that this velocity is the one, the relative velocity is the one that we are going to represent here or draw here. This one, again, it should be represented or drawn between 2 points, point A or point B. So it should be in the velocity diagram drawn from either point A or point B, depending on which point is already located or defined in the velocity diagram. Here, we already located point A. So from point A, I'm going to draw point B. Very simple. Make sense? What is the magnitude? We have no clue. It is unknown. But how about the direction? You're going to stick to the same procedure. Define the direction, draw a line, measure a distance. The same procedure. So the direction, it should be perpendicular to the R3, follow the direction of omega 3. But we don't know what is the direction of omega 3 because we don't know its value. It is not given. But anyway, so the only option that I have for this velocity vector is just to draw a line that is perpendicular to the R3. This line should be locus to the other point. So in case that you have a velocity vector with unknown either magnitude and direction, in many of the cases, especially if this is a length that rotates, so in many of the cases, the magnitude, in case that the magnitude is unknown, you can only draw one line, one thing only, which is a line. This line, in case that this velocity vector is belong to a length that rotates, whatever general motion or fixed point, so it should be perpendicular to the R of this length, right? So what does it mean? And it should be represented from either A or B. We already have point A. So what does it mean? From point A, you're gonna draw a line perpendicular, according to the plan here, perpendicular to the R3, follow omega 3. Forget about omega 3 for now. Just perpendicular to the R3. So this is R3. And try to draw a line completely perpendicular. So as you can see here, I align this black line to this R3. Make sense? I align this black line to this R3. So if I draw line, this line definitely will be perpendicular to the R3. As you can see, this angle will be completely 90 degrees, right? So this line, this light line that I draw here, this line will be locus. This line should be locus to the this line will be locus to the other point, which is point B. Like it means that point B should be located somewhere over this line. Why point B, not any other point? Because this link has been set up between 2 points, point A and B. And we are talking about VB relative to A. So if we have A, we are seeking B. So B, it should be somewhere over this line. And that's it for this link. We've done this link. We nothing more can do for this link. So what we're gonna do next, move to the next object, which is the slider. For the slider, this is slider that simply slides over the ground. Whatever horizontal, vertical, or inclined is gonna be the same. So its relative velocity component or vector, it has magnitude which is unknown. So this is unknown magnitude, but we are pretty sure of the direction that it should be parallel to the R4. And this one, it should be represented or drawn from between O and B, or drawn from either O or B, depending on which point is given or known in the velocity diagram. In the velocity diagram, we are pretty sure that point O is 0. So, and that's why point O is already located here, which is the OV point. So from this point, I'm gonna draw a line that is parallel to the R4. And in the diagram, R4, it is horizontal. Or in the position polygon, it is horizontal here. So what I'm gonna do from this point O, I'm gonna draw a line that is completely parallel. Make sure I'm aligning this vertical line with the vertical axis, also making sure that this line is parallel to this line, to draw a line that is completely parallel, right? This other line, this horizontal line, gives another locus of the other point, which is point B, because this one should be set up between B and O. This is the thing that we are already drawing, right? So we do have O and we are seeking B. So we draw a line from O horizontal parallel to the R4. This is gonna give us another locus for point B. So as you can see, this is one locus for point B, and there is another locus for point B. Both they're gonna intersect at this point. This is the point of intersection of this locus to this locus. Both gonna intersect at the same point, at one point, which is point, this point definitely will be point B that we are really seeking. So if you simply set up a line here, this line is set up between O and B, right? This line is, or vector is set up between O and B. So this should be B relative to O vector, as you defined it as B relative to O, so it should be B relative to O. But you should understand that the direction should be from O to B. So from O to B, so it should go in this direction. Make sense? And let me move this one outside. Here, this is gonna be VA relative to O2 vector. This one I just wrote, this one belongs to this vector. Then I'm gonna connect A to B, because I need VB relative to A. So there should be a velocity vector set up between points A and B. So that's why I'm connecting these 2 points A and B. And the direction of this one is VB relative to A. So it should be VB relative to A, means moving from A to B, moving from A to B. This is the VB relative to A direction. So these are all, this is the velocity polygon we've done. We agreed from the beginning that we're gonna end up with 3 lines, and we got the 3 lines, and there should be the velocity polygon, kind of. I'm just using this color, which is not necessary to do the same actually, but this is the velocity polygon here. That we do have 3 edges. These 3 edges, each one is a velocity vector. Some of these velocity vectors are already fully defined, and some of them already known. The known things are the VB relative to A magnitude and the direction of omega 3. What is the direction of omega 3? The same issue for this one. So your objective, once you finish the velocity polygon, you're gonna write here from the velocity polygon. Your objective is just to find the unknown. The first thing is VB relative to A vector equals, or just the magnitude. Forget about the vector for now, just stick to the magnitude. The magnitude, which it should be the R3 omega 3, how much it is. VB relative to A, we already got it here, which is this line. Measure this line here. If we measure this line, it will be 10, 20, 30, 45 millimeter, right? So it's gonna be 45 millimeter, but it should be converted it should be scaled back because I use the 75 inch over second. It should be 50. So now the 45, it means that I do have 45 from the graph here, from the drawing. So what should be? It should be 45 times 75 divided by 50. So it should be 45 times 75 inches divided by 50. This should give us the VB relative to A, the magnitude, times 75 divided by 50 gives us the 67.5 inch over second. Make sense? So we got here the VB relative to A vector, or the magnitude. Okay. We got the magnitude here, right? Then what we have to do, this one equals R omega 3. So what should be omega 3 then? The value. How about the value of omega 3? Omega 3, it should be the 67.5 divided by R3. How much is R3? R3 from the position analysis was 10 inches. It was 10 inches. So divide by 10, this is going to give us definitely 6.75 radian per second. Make sense? So this is the value of omega 3, but how about its direction? The direction of omega 3 depends on the direction of VB relative to O as represented here. So if this is the direction of VB relative to O, it goes down, it moves down. It means that omega 3 should be going down, because this one, it should be perpendicular to the R3 as we put the plan there, right? And it should rotate in the same direction of omega 3. So this indicates that omega 3, it should be rotating down in this direction. This direction is given here as given it is clockwise direction. Make sense? Why? Because it moves down. So it means that this should be clockwise direction. This is the correct direction of omega 3, and this is the magnitude. So we got everything regarding this link. Now we're going to move to the second unknown. This is the first unknown. The second unknown, which is the VB relative to O vector. And you should understand that VB relative to O, forget about the vector again. This is the sliding velocity of the slider itself. But this is the linear velocity due to the rotation of the link. This is the sliding velocity of the slider, which is VB relative to O. Your objective is just to measure this distance here, which is 40 millimeter exactly. So it means that it should be 40 millimeter. If we decided to convert it, so it will be 40 times 75 divided by 50. If you did the multiplication, this is going to give us 40 times 75 divided by 50 gives 60 millimeter, 60 inch per second. This is the value for this sliding velocity. And remember this, there is no omega, there is no specific formula for this one, it's just a value. So the value is just 60 inch per second. But how about its direction? Is it the same direction as R4 or opposite direction of R4? As we mentioned, it should be parallel to the R4. Parallel does not mean it should be in the same direction or in the opposite direction. We have no clue. But here we found that the direction of VB relative to moves to the left, opposite to the R4. So it is already going to the left. It is going to the left in this way, opposite to... Right, so now let us move to the acceleration analysis. We have finished the velocity analysis and we drew the velocity polygon. And if you remember that we already explained 3 different cases. So we're going to consider the 3 cases, but in terms of the acceleration analysis. As we mentioned for the velocity analysis, we're going to deal with 4 different cases in general. The case that you have a link that can rotate about a fixed point, a link that can do general bearing motion in addition to the slider. In addition to the 4th case, which is not included in this example, it will be included in the next example, or example 2, which shall be covered in another video. That the case that you have a slider over a link. So in this example, we're just going to consider these first 3 cases: rotation, link that do rotation about a fixed point, link that do general bearing motion, and the slider that moves over the ground, whatever it is, horizontal or vertical, or inclined ground, or even if it is curved, as I'm going to show you for the acceleration part, or especially it will be shown, we're going to need it for the case of the slider over a link. But forget about this point for now. generally speaking, in case that we do have these three simple cases of the lengths, and we are interested in figuring out or doing the acceleration analysis of this mechanism. So we're gonna stick to the same procedure. We're gonna do the same thing that we did for the velocity analysis. Even we're gonna write the same equations, not exactly the same, but we're just gonna follow the same plan. We're gonna put the same plan, but for the acceleration part. So what we're gonna do right now, we're just gonna move to the third step, which is the acceleration analysis. So we're gonna repeat the things that we did here for the velocity. We started from the length with the length that already given angular velocity. The angular velocity here, acceleration, which is alpha 2 is already given by 150 radian per second squared. And this angular acceleration was given for length 2, so I'm gonna start with length 2. Again, length 2, it has 2 points, point O2 and A. It means that you have to set up the acceleration vector, or the equation of the acceleration that define the relative acceleration between these 2 points, point A and O2. Make sense? So, and this equation, it's gonna be typically the same. Generally for the case, and this is the first case, in case that you do have a link that do rotation about a fixed point like point O2, and the other point is just point A, and this is the position vector, which is R2 vector. So this is just rotation about fixed point. So for this case, and as you can see, the 2 points are point A and O2 and A. So directly the equation for this length, will be, you can either start, refer, or define VA, like as we did for the velocity. We can start with writing VA out on the left side, or VO2 on the left hand side. The same thing for the acceleration. But try to stick to the thing that you already did for the velocity analysis. I started with VA here, so it is better to start with AA as a vector. It should equal to the acceleration of O2 as a vector plus some relative accelerations. And the relative acceleration again is the thing that we are going to draw in the acceleration diagram or the acceleration polygon, as typically as we did for the velocity analysis. Make sense? So, but here, if you remember from the dynamic class, that any length that rotate, and even if you remember from the complex algebraic method that we already covered so far in this course, that in case that you have a length that rotates, generally whatever it rotates about a fixed point, or if there is no fixed point, it means that the length doing general motion, it will have two components of the acceleration. One is normal and the second one is tangential. So you have to remember the thing. It means that we have two components here. One is normal and the other one is tangential. The normal of what? The normal of the A relative to O2 and A relative to O2 vector and vector. These are the two components of the acceleration. One is normal and one is tangential, and these two components here are the two that shall be drawn. But here in the velocity analysis for length that do rotation, we had only one component of the velocity. Now we have two components of the acceleration that we have to draw them. Make sense? But as we did here, we have to write an expression for this relative velocity, right? Here, the same thing for the relative acceleration. These two components, we need an expression for each one. So it means that the acceleration, we knew from the dynamic class or even from the complex algebraic method that the magnitude, I don't know why I write about the, okay. So the magnitude of the normal component, it should be R times omega square, right? And since we are talking about element 2 or length 2, it means that it should be R2 times omega 2 squared. What is omega 2? This is the angular velocity of the length, which is already given by 30. Or even if it was not given, since you finished the velocity analysis, you should have value. You should get value for the omega 2. It means that we already have a value for omega 2 anyway. And R2, this is the length of this length, which it should be obtained using the position analysis. It means that by moving to the acceleration analysis, these two data should be given. It means that omega A normal anyway will be number. A normal cannot be unknown. A normal all the time should be known, because this A normal depend on R, which is you gonna get it from the position analysis, and omega 2 that would be given, or you gonna get it from the velocity analysis. It means that R to omega 2 anyway will be given or will be known at this instant of time. So how much is R2? We already got it by 2 point, or already given by 2.5 inches, so it is 2.5 inches times omega 2, which is already given by 30, so it will be 30 squared. Make sense? If we did the calculation, we shall end up with a value for the A normal. So A normal will be 2.5 times 30 times 30. This gives 2,250. The unit, it should be in inch over centimeter square. So this is the normal component, and it has a value already. This is for the magnitude, this is for the value. How about its direction? You should understand that it should be opposite to R2 vector, as we discussed in the complex algebraic method, or even from the dynamic class. Like all the time, the normal component should be opposite to the R2 as long as we have a straight length. And in case that we have curved length, we're gonna talk about this issue later. But for now, we do have a length that rotates about a fixed point, and this length is a straight length. So in this case, definitely the A2 relative to O2 normal will be R omega square, and it will be all the time known. It cannot be unknown, and all the time it is opposite to the R of the same length that you're already considering, which is length 2. Make sense? This is the first component that shall be drawn. And the second component also that shall be drawn is the AA relative to O2, this relative acceleration tangential component as a vector. Right? Again. Alright, so here I'm talking about the magnitude. The magnitude, it should be the R2 alpha 2. If you remember from the dynamic class or the complex algebraic method, that the tangential component, it is R times alpha. What is alpha? This is the angular acceleration of the length 2. Since I'm talking about length 2, and alpha 2 is already given here by 150 radian per second square. So what does it mean this? It means that R2 already got it by 2.5 times 150. If we did the calculations, we're gonna end up with 2.5 times 150. This is gonna give us 375 inch over second square. Make sense? So this is the tangential component, and this is the normal component. What is the direction of the tangential component? It should be perpendicular, generally. It should be perpendicular to the A normal, A relative to O2 normal vector. And since we don't have a straight length, and R and A normal is already opposite to the R2, it means that it is kind of parallel to the R2. It means that also I can say that the tangential component, it is perpendicular to the R2 vector and follow the direction of omega 2. Follow the direction, of alpha 2. It is very similar to the velocity, the relative velocity of the same length. The relative velocity of the same length, it's gonna be a velocity that it should be perpendicular to the R. In addition, it should follow the omega of this length. Here it should be perpendicular to the R and follow the alpha, the angular acceleration of the same length. So these are the two components that shall be drawn. How you can draw them? These two components should be drawn from either point A or point O2. This one also shall be drawn from either point A or O2. So since we do have O2 is a fixed point, so its acceleration will be 0. And again, as we did for the velocity, we are going to define OA, which is the origin point, origin of the acceleration polygon. So what does it mean? It means that any point that belongs to the mechanism with a 0 acceleration, it should be considered to this point. Typically the same like the point OV that we defined for the velocity diagram. This is the origin point of the acceleration polygon or acceleration diagram, and any point with a 0 acceleration should be considered to this point, like point O2. So definitely point O2 will be known. So in this case, this one, it will be drawn from point O2. We're gonna draw from point O2, right? So basically both are given, both are fully defined in terms of direction, in terms of magnitude, because the direction of alpha 2 is already going in the counterclockwise direction. So how we can draw these two components? In the previous, in the velocity, we had only one component of the velocity. Now we have two components. So what does it mean? This, it means that, for example, if, and it's gonna be clear when we draw, assume that this is like point O2. We agreed that point O2 will be considered to OA, so we are pretty sure that we do have a location for O2. Then from O2, you're gonna draw, let's say that this is the direction of A normal, you're gonna draw A normal. Then you're gonna draw the A tangential to be perpendicular. As we said that generally it should be perpendicular to the A normal, which is perpendicular to the R2. Then you're gonna go perpendicular to the A normal to draw the A tangential in the same direction of alpha 2. That the perpendicular to A normal, it would be either this direction or this direction. Right? Assume that the direction of alpha 2 is this direction. So I'm gonna go down. This is gonna give us the A tangential. If we connected these 2 points together, if we connected these 2 points, this is the end point. Like for example, if this is O2, this definitely the end of the tangential, you're gonna draw the normal, then tangential, you're gonna end up with the point A. Make sense? I have to draw the 2 components to locate point A, because these 2 components should be set up somehow between 2 different points. These points are O2 and A, but you should have normal that is opposite to the R2 direction, then you should have the tangential component, for example. These directions are not exactly the same like this one, but just assume these directions for now. Make sense? The other option here that I started drawing the A normal, then I draw after the A normal A tangential, but you can start with drawing the A tangential first. For example, the other option that I can draw the A tangential in this way, then I'm gonna take the A normal, so this is gonna be the A tangential, and you're gonna draw the A normal after the A tangential to be normal to the A tangential itself. Make sense? So it means that generally for a length that rotates about a fixed point, that the normal and the tangential component, they should be perpendicular to each other. And you can start with either the normal component, then the tangential, or the tangential, then the normal, it's up to you. Okay? But conventionally, or as we agreed, in many of the cases, in all the cases, A normal will be known. It will be either value or 0. And the tangential, it would be known or unknown. It depends on what? It depends on the given data in the in the problem itself. So in case that A tangential is unknown, you cannot start with drawing the tangential then the normal. You have to start with the normal then the tangential. So generally it is preferred to start with the normal all the time, since all the time it will be known, and then you're gonna draw the tangential component. In either ways, whatever you start with A normal then tangential, or tangential then normal, you're gonna end up with the same point. You're gonna move to the same point, which is point A. So for example, if someone started with A normal, he gonna draw this line, then this line, so he gonna end up with this diagram. The other guy who's gonna draw the opposite, he gonna end up with the mirrored diagram, but both are correct because you're gonna end up with the same point. And if I ask you how much is the absolute, this link between them, this line between them, this line, it should be the acceleration of point A with respect to O2 vector. This is the magnitude, which it should be the square root of the A normal square plus the A tangential square. This is the resultant one, because you have 2 components, and this is the resultant component of both of them. This is the meaning of these 2 components, but we're gonna do the same here over the acceleration, polygon or acceleration diagram. But generally this is what we're gonna do or consider, or this is the plan how we're gonna draw these the acceleration component for a length that do rotation. For a length that do general motion, it is typically the same. For a length that do a general motion is gonna be identical, which is gonna be the second link here. So this is the plan for now for the first link. Moving to the second link, which is link number 3. This link again is set up between 2 points, point A and B. So I'm gonna say that I do have this link, which is link 3, that is set up between 2 points, point A and B, and this is R3 direction, right? And the equation for this link, it should be definitely either you can refer A to B or B to A, it doesn't matter, it's gonna end up with the same relation and the same result, but try to stick to the thing that you already did for the velocity analysis. For the velocity analysis of this link, we used the first equation that we wrote the VB on the left side and the others on the right hand side. So we're gonna do the same. AB vector equals AA vector plus, again, there should be normal component and tangential component. Since this link is doing rotation, this is doing general plane motion, which is rotation and move. There is no fixed point. Because of the rotation, we're going to have normal component plus tangential component, but this should be B relative to A, since we are talking BA, so B relative to A and B relative to A, just BA vectors in this way. And again, these are the two components that shall be joined. So the normal component, as we knew before from the dynamics or the complex algebraic method, that it should be R times omega squared, like even what we did for the previous length, right? The normal component, which omega for length 3, since we're already talking about length 3, so it should be R3 omega 3 squared equals. How much is R3? R3 we should get it from the position analysis, which is already given by 10 inches. So we do have 10 times omega 3 squared. We got from the velocity analysis omega 3. So we cannot do acceleration analysis unless we finish first the velocity analysis of this diagram. We got omega 3 here equals 6.75 radian per second, so it's going to be 6.75 squared. If we did the calculations, this is going to give us 6.75 squared times 10 equals, this is going to give us 455.625 inch over second squared. Make sense? And again, the normal component, it is fully defined here. What is the direction of this one? All the time it should be opposite to the R3 vector. Okay? All the time it is opposite to the R vector, the position vector of the same length. Now we're going to move to the tangential component. AB relative to A tangential. How much it is? Equals. If I ask you how much is BA relative to A tangential, the equation, the formula of this one, it should be R alpha. But which R, which alpha? It should be R3 alpha 3. Why 3? Because I'm talking about length number 3. Make sense? How much is R3 is already given by 10 inches up here, right? But how much is alpha 3? We have no clue. Alpha 3 is unknown. So this is the first unknown. And remember that for the acceleration analysis, we are only limited for just 2 unknown. This is the first one of them. Make sense? So the tangential component is unknown in terms of magnitude, but we have like indication about the direction of this one. This direction of this component, it should be perpendicular to the R3 vector, or in general it should be perpendicular to the A normal, right? Which is automatically will be perpendicular to the R3, since A normal will be opposite to the R3, and it should follow the alpha 3. It should follow the alpha 3, which is already unknown. Make sense? So it is very similar to the case that we experienced for the same length for the velocity. We are repeating the same issue for the acceleration, but here we do have 2 components. So these are the equations, and again remember that there should be joined from either point A or B, right? From either point A or point B. It depends on which point that is going to be located within the acceleration diagram, but we are expecting that point B will be located, or point A will be located first. We're going to define point A first, since we don't have this link is fully defined. So it means that starting from O2, we're going to find point A, then from point A, we're going to find point B, right? But point B will not be found completely through this link because it has some missing data here. It means that we're going to end up with one locus, but we need another locus for the same point, which is point B. So that's why we have to consider the third object. The third object here that we have is the slider. And for the slider, as we did for the velocity, what we did for the velocity analysis for the slider, this was the equation for the slider, right? So we're going to use typically the same equation for the acceleration. So again, in case that we have a length that rotates about fixed point or general plane motion, these are the first 2 cases. For the acceleration equation, it will have 2 relative velocity acceleration components. One component is normal, the second component is tangential. All the time, the normal, it is R omega square, and all the time it is opposite to the R of the same length that you're already considering, and all the time it will be given, it will be known. But the tangential component, it is r times alpha. This is the magnitude, this is the value, and its direction all the time, it is perpendicular to the r but follow the alpha of the same length. It has two options. It would be either given or it would be unknown. It depends. But all the time normal will be known, right? This is the second case for these two cases. But in case that you have a slider that moves over the ground, whatever, horizontal, vertical, or an inclined surface. So the equation for the slider, the equation of a slider that moves over the ground, like slider B, we set up R4 for this slider, right? R4 vector, and this R4 is set up between 2 points in the mechanism as already given here, which are point O and B, right? So we already have R4. For this length, the equation, it's gonna be typically the same like the equation of the velocity analysis for the same slider. Here there is no normal, there is no tangential because there is no rotation. This R4, it won't gonna be rotating, right? So it means that we're gonna have the acceleration of point A vector equals the acceleration of point O vector, which it should be 0, plus the acceleration of point A relative to O vector, and this we're gonna end up with just one relative component, or one component of the relative acceleration of point B with respect to O, which it should be the sliding acceleration. This should be the sliding acceleration of this slider. Make sense? And this is the thing that we have to draw. So what is the formula for AB relative to O vector? It has no formula, it has no equation, or has no law, right? Typically the same as we did for the velocity analysis, and in many of the cases it will be unknown. In many of the cases it will be unknown unless it will be given. Like he literally mentioned in the problem that the sliding velocity or the sliding acceleration of the slider is given by this number, right? So in this case automatically the AB relative to O will be given, and you're gonna plug the value here. But in case that it is not given, at this case, in this example, this sliding or acceleration is not given, so it means that it will be the second unknown. And as you remember, in the acceleration analysis, we are limited for just two unknowns, which gonna be these two unknowns here that we are seeking their values. But what about the direction of this this sliding acceleration? Again, it should be parallel to the R4 vector, typically the same as we did for the velocity part. We wrote that it is parallel to the R4. Parallel to the R4, again, it means that it is not necessary to be in the same direction as R4 or opposite direction to the R4. It depends. It depends on what? It depends on the data that and after we draw, we can identify the exact direction of this acceleration. An important knowledge here about this acceleration, if he literally mentioned in the problem that the slider moves with a constant velocity, automatically this acceleration should be 0. So again, if he mentioned that the slider moves or slides with a constant velocity, it means that the acceleration component of the slider should be 0, because the acceleration, it is a rate of change of velocity. So if this slider is constrained to move at a constant velocity, so it means that this acceleration component will be 0, and in this case it will be like given, right? But here he didn't give any data or any information regarding the sliding velocity of this slider, whatever it is, constant or variable. So I'm gonna deal with it like a variable, and it means that there should be a value for the acceleration, and we are seeking this value of the acceleration, sliding acceleration of the slider. So we set up, this is the plan, this is what we wrote here, this is for the velocity. What we wrote here, we wrote 3 equations. This is the first equation for the first link, and this is the second equation for the second link, and this is the third equation for the third object, which is the slider. So these are the 3 things. So we are expecting doing the drawing 3 times. But for each one of these drawings, like this one, here we're gonna draw 2 lines, not just 1 line, right? Because we have normal and tangential. Here we're gonna draw 2 other lines. We have normal and tangential, and the normal has a value, the tangential we have no clue, right? But normally we're gonna have like 2 other lines. In addition, we can have only 1 line for the slider that it should be represented in the acceleration polygon. So the acceleration polygon should include 5 lines in total. Make sense? So we have an initial view what it should be represented in the acceleration polygon, and then we're gonna move to the drawing sheet. So we're gonna keep this data here on the side because we're gonna use them. Then let us move to the acceleration polygon to the drawing sheet to draw the acceleration diagram. So in the acceleration diagram here, this is the acceleration polygon. Just let me change this once it's set. Delete. Alright. So again, we have to specify a point. This point, it should be the OA point, which is the 0 point, the start point of the acceleration polygon that we're gonna consider here, right? So, but you have to have an idea about the scale of the dimension. So we do have here some data, some numbers. We do have 2,250 and we do have 375 and we do have 455. These are the three numbers. It means that we have to do scaling here. We're gonna do scale, and the lower value or the smallest value of 375 millimeter, I'm gonna draw this one like, let's say 10 millimeter, for example, 10 or 15 millimeters. Then how about the 455.6? What it should be? This should be, I'm sorry, this is the inch over second square, because this is the acceleration. This should be inch over second square. This inch over second square. So what it should be in terms of millimeter? The same thing for the 2,250. How much is gonna be? 2,250 inch over second square. How much it should be? So I'm gonna calculate the 250, the 2,000 first. This should be the 2,250 times the 15 divided by 375. So it's 15 times 250 divided by the 3. It's gonna be 90 millimeter. It means that this value, it will be represented 90 millimeter in the drawing, and the 455.6 times 15 divided by the 375. This is gonna give us the 18.22 millimeters. It makes sense? So these are the scale value that I'm going to use for the creating or generating the acceleration diagram. So as you can see, the maximum dimension, it is 90, the smallest dimension is 15. So you have to, for example, if I start to draw in this side, it means that probably you're going to find a space to finish the drawing. And it is advised, especially this 255, it should be opposite to the R2. This value should be opposite to the R2, and R2 is going up, right? It's going up. It means that the direction of this normal, it should be going down. So you should have a space in the down direction. So it means that if I started, for example, if I consider that OA, which is the origin point, the start point of the acceleration polygon at this point, and you started moving down opposite to the R2, as already given here, moving down opposite the R2, you aren't gonna find a space. So that's why it is advised to start O2 at any point up there. You can even remove this one, and I can start creating the O2 even, and no problem that you have intersection between the different diagrams, that is fine. I'm gonna start with OA from this point, right? Then I'm gonna stick to the plan, starting with the first line here. The first line, I'm going to draw two components. One is normal, then the tangential, or you can start with the tangential, then the normal, as long as both are known. But conventionally, as we agreed that the normal all the time will be known, so it is better to start with the normal all the time. Anyway, I'm going to start with the normal, and its direction, it is opposite to the R2. And this is its value, which is 2,250, which I'm going to draw this value as 90 millimeter. So what are you gonna do? You're just gonna draw a line from the either point O2 or point A. O2, this is the point that we already have, because this OA, it should be, O2 should be considered to this point, also point O should be considered to this point, as long as these are two fixed points in the mechanism. These two fixed points with zero accelerations are O2 and O, so both of them will be over the original point of the acceleration diagram. So this one, it should be represented, drawn from O2. I already have O2, so starting from this point, I'm gonna draw a line opposite to the R2, parallel to the R2, but going in the opposite direction. And the length of this line, it should be this value, which it should be 90 millimeter after the scale. So I'm gonna use the triangle to draw a line. So how could I find a line that is typically parallel to this one? You can draw any other line, very light line that is parallel. Make sure that one of these lines, black line, is already inclined over the R2, and draw a very light line here, because I'm not using this one. I'm just gonna use to have a copy, another parallel to this one. So I draw a line here. I'm gonna draw a parallel to this line at this point, in this way. Just make sure that this line is parallel, and draw a light line going down in this direction. So over this line, I should measure 90 millimeter, and the end of this line, from the end of this is gonna give me the normal only. The end of this line, it will not give us the point A. No, we still have tangential. Then after the tangential, the end of the tangential, we're gonna find the point A. So I'm gonna measure 90 from this point. 90 should be up to here. This is the point here. So if I draw a line, this line, I'm gonna make it very thick line, just to distinguish this line from any other line of the velocity diagram. So this component, it should be the A normal of A relative to O2 vector, right? And from the end of the normal, keep going. This is not point, this point is not point A. You have to still keep going, because we still have another component, which is the tangential component, that it should be perpendicular to the R2, following the direction of alpha 2. What is the direction of R2? R2 is already going up. The R2, this is the R2, or simply you can consider like it is normal to the normal component. It is perpendicular to the normal component. So we got the normal component. Draw a line that is perpendicular, follow the direction of alpha 2. Remember that alpha 2 goes in the counterclockwise direction, so this should be alpha 2 direction. It means that I have to go up. So what I'm gonna do from this point, I'm gonna draw a line that is perpendicular going up. Going up how long, how much? This distance, it should be 375, which it should be here according to this number as 15 millimeter. So I'm gonna go up here 15 millimeter. So I'm gonna draw a line with 15 millimeter and mark a point. This point, this new point, and I'm gonna make this one thick. This point, then it will be point A, that I draw normal. Then tangential, I got point A, right? And this component, it should be the A tangential of the A relative to A. It should be the A tangential, should be A relative to O2 tangential vector, right? So now we located point O2 and point A, and we have done of the first curve. Make sense? Which is fully defined. Then we're gonna move to the second equation. The second equation, it has two also components, one normal, one tangential. The normal is known, so I'm gonna start with drawing the normal. But this normal should be drawn from either point A or point B, depending on which one is already given here in the diagram. So the point that we already have so far is point A. We don't have point B. Remember that this green thing belongs to the velocity diagram. Okay, I can move this one down, so I think I'm gonna have some space just to not confuse you. So okay, but anyway, let us continue. So this is the normal and tangential. We got point A here. This is point A. Now we're gonna draw the normal component. The normal component, it should be opposite the direction. It should be drawn from point A, since we have point A, opposite to the R3. So this is the R3 direction, right? And with this value, right? So let us draw first a line that is opposite to the R3. This is the R3. So I need to draw a line that is parallel to R3 and go opposite. It means that I'm gonna push up in this direction, right? So I'm gonna draw first a line here. One line here in the middle to be parallel to the R3. Then I'm gonna draw another parallel to this line from point A. Just make sure that you use these lines to draw correct parallel lines. Then this is the line that is opposite. I'm going opposite to the R3. how long, how much of the distance it is 455. The 455 it became 18.22. It means that nearly it's gonna be 18 is fine. So it means that if you draw a line, measure here a line with 18, which it should be like up to here, mark a point, then this should give us the normal. This is just the normal component. This is just the A, B relative to A normal component. Make sense? This should be just the A. Forget about the dimensions, the directions for now, but you should understand that this line belongs to the A, B relative to A normal, as I am already using it here, right? B relative to A normal vector. Then you're gonna draw the tangential, but the tangential is unknown. But I know its direction, that it should be perpendicular to the R2, R3, but which direction exactly depends on alpha 2, which we don't know the value of alpha 2, even the direction, right, of alpha 3. So it means that you have no option except just draw a line that is perpendicular to the R3 from the end point. I draw the normal from this point. You have to draw the tangential that it should be perpendicular. So simply perpendicular to the R3 should be perpendicular to the normal, the A normal itself. So simply I'm just gonna draw a line. This line it should be locus. This line it should be locus to point B. It means that point B it should be located over this line somewhere. And by this I've done of the second equation. Now we're gonna move to the third equation, which is very simple equation. It has B relative to O2, so relative to O, so it would be drawn from either point B or point O. The point that we already have here, we don't have point B yet, but we have point O, which it should be this point. So starting from this point, you're gonna draw a line that is parallel to the R4. Parallel here doesn't mean opposite or the same direction. We have no clue because this acceleration is not given. So we're just gonna draw a line that is parallel to the R4. The end of this line should give us point B, which we have no clue where is point B yet. It means that this line is going to give us a locus, a second locus to the point B. The intersection of this locus to the locus that we got here from the previous equation, we're going to end up with point B. We can locate this point B. So what I'm going to do, I'm just going to draw a line parallel to the R4. And R4, it is horizontal. It means that you're just going to draw a line from this point O, that is horizontal line. This second line, so I'm just going to draw these two lines with the red color. This is the first locus and this is the second locus that we got from this point. So one locus, this is locus for point B, and this is another locus for point B. Both this line and this line, both they are going to intersect at a point. This point definitely will be point B. Then simply what you're going to do, you're just going to go over. I know that it is kind of confusing the drawing, but I'm not caring about the velocity diagram that I already represented before. So then you're just going to go over this line. So this line, this new line here, this new line, and this new line, this should be the tangential component that we didn't find its value in the beginning, and this should be the sliding acceleration, right? Because it is set up between B and O, so this should be this component, this line, it should be acceleration of B relative to O vector, and this line, it should be, we're already moving from A to B or B to A through normal and tangential. It means that this should be the tangential component. This should be AB relative to A tangential vector. Make sense? Now we have to work over the directions of these different components. Starting with the AB relative to A, since we are talking about B relative to A, it means that we have to move from A to B. So we have to move from A with a normal, from A, this is the normal component, then we're gonna move to B. Moving from A, this is the point A. A normal, then A tangential, so this should be the direction of these two components. How about the AB relative to A? It should be moving from O to B. From O going to B, so this should be the direction. The direction of this one, it should be going from O to B. Make sense? Then what you're gonna do, we almost done. Your objective is just to find the unknowns. So using the drawing sheet, another drawing sheet from the acceleration polygon, you just gonna measure the unknowns. The unknowns that we already have are two things. For the second equation, we already have the AB relative to A tangential, which it should be R3 alpha 3. You just gonna measure this value in this value. In addition, we do have the AB relative to O vector, or the magnitude of this value, how much it is. We're gonna get these two values from the joint. So going back here, the B relative to O, which it should be the distance between B and O, if you just measure this length, we're gonna get it like 65. So this value is 65 millimeter on the graph, so it should be scaled back. Also the A tangential, it should be this value, which is gonna be like 33, right? It's gonna be like 33 millimeter. So this value should be scaled back. So we're gonna multiply this 33 times. It will be multiplied times the 375 divided by 15. This is gonna give us how much in terms of inch over second square, because this is acceleration. Also, we're gonna multiply this value 375 over 15. We're gonna end up with inch over second square. This one will be the sliding acceleration. This one will be the tangential component of the acceleration of the length number 3. From this value, we can find, from this one, we can find how much is alpha 3. So by dividing by R3, which is already 10 inches, this R3 is already 10 inches. So doing the calculation, 33 times 375 divided by 15, this is going to give us 825 inch over second square. If we divide it by 10, this should give us the 82.5 radian per second square, that it should be the angular acceleration of length number 3. How about the direction of alpha 3? Is it clockwise or counterclockwise? We're gonna figure it out from the diagram here. The tangential component is going up, right? And it should be perpendicular to the R3. So it should be perpendicular with a 90 degree to the R3 here, and it pushes up. So what does it mean it push up? It means that the direction of the alpha 3, it should be going up in the counterclockwise direction opposite to the alpha 3 or omega 3. So alpha 3, it's gonna be counterclockwise direction according to the figure. How did we know this? Because it's going up in this direction. Make sense? So this is the alpha 3. How about this value? Just calculate the value, and it's gonna be it for this problem, which is gonna be 1625 inch over second square. And this is gonna be the sliding acceleration of the slider. Make sense? So we have done of this example. This is the drawing sheet, and all of these are different writing sheets, right? That you're gonna use them to describe the complete kinematic analysis of the mechanism. So this should be your response for a question like this one. So through this example, we consider 3 different cases of the objects of mechanism. Like you have a link, as I mentioned, that do rotation about a fixed point, a link that do general motion, and slider. All right, in the next meeting, we're gonna solve, or another video, the next video, we're gonna solve this example that include the 4th case, that you'd have a slider that slides over a link, and the link in the meanwhile is already rotating. So we're gonna discuss this case in another video. But for this one, for this video, and the previous video, we discussed how we can do position analysis graphically. Through this video, we consider a complete example on the position, velocity, and acceleration analysis. Again, try to stick to the procedure. Try to put the plan first. Write the equations so you can understand exactly how you can draw these or create these drawings in this way. And don't be confused, because if you couldn't able, you have to try to doing these things by hand. If you try to draw the graph, you won't gonna understand anything. Okay, so reading the graph, it will be too confusing unless you try to do it by your hand step by step. So that's why it is advised to write the equation first, then your objective is just to use the equations and draw them using the over the drawing sheet. All right, So this is for this example. Again, the next meeting, the next video, we're gonna solve this one. Also, we're gonna have more videos for the graphical method as more practice over this method for the kinematic analysis of mechanism using the graphical method. Alright, so thank you and see you in the next video.